Hey guys, wanted to talk to you real quick today about math and what kind of math we'll be using in here, calculator that you need, whatever. So it's just kind of a little review thing today, but let's see what we got. First up, we need a calculator. You got to have a calculator. You can bring a slide rule if you know how to use it, that's fine, but an abacus, whatever, you got to have something here. And the two big options would be any kind of graphing calculator is fine. That's what a lot of people already have, and that will be fine. A scientific calculator will also be fine. It's got to have a sine, a cosine, and a tangent button. It's got to have a square root functionality to it. I like the ones where there are two lines where you can see what you're typing in, hit enter, and it processes the whole expression all at once. But that's up to you. Either one of those will be fine. This little blue guy up top is about $10 at the big box store, so if you don't have the graphing calculator, you don't need to go buy one of those. Something up here will be just fine. Okay. There are a couple things that people do with calculators and get messed up, so I wanted to talk to you real quick about that. In this first little part here, there are two settings on your calculator. You can either set to degrees or to radians. Now if you haven't worked with degrees or radians or whatever, that's fine. I've got my calculator right here, and if I'm using one of these sine or cosine functions, sine of 52 degrees, right, and I hit enter and I get an answer. That's the answer that I think I'm looking for, but there is also here on the mode button, you can come down and select radians, and when you do the sine of 52 degrees, you get a very different answer. You want to be set to degrees. All semester long for me, set it to degrees. Now if you're in a trig class simultaneously and you're having to switch back and forth, that's fine, but you really need to make sure you know which one you're in. That's the easiest way to mess yourself up. One more time here, hit the mode button, hit down, down, right, and that get the blinky thing on degree, hit enter, it steps it over there, and then second mode will get you out of that, and you'll be right back where you were before. Okay, so watch out for that. Set your calculator to degrees. Over here on the right hand side, there's a little bit of extra stuff. Order of operations is really important. Remember, please excuse my dear Aunt Sally, the calculator is going to try to do anything inside parentheses first. It's going to try to do exponents second. Any kind of multiplication division comes third, unless it's already been done inside parentheses, and any kind of addition subtraction comes last. So just kind of think about the way that the calculator is going to look at it when you put something in. Here's a problem right here, 12 divided by 2 times 3. Now you know that 2 times 3 is really a 6, and 12 divided by 6 is 2. So the correct answer here is 2. But I've put this into the calculator 3 different ways here, and I got 2 answers that are correct and 1 that's incorrect. So thinking about this top one and why it's wrong, calculator sees 12 divided by 2, and it says, well, 12 divided by 2 is 6, and then right here times 3 is 18. It does order of operations. It says multiplication. There's a division, there's a multiplication. It's all the same importance. Just do it left to right. You get the wrong answer. There are 2 ways to do it correctly. You could say 12 divided by parenthesis 2 times 3, and that parenthesis will hold it together, make that a 6, and 12 divided by 6 would be 2. Or you can say 12 divided by 2 is 6, and then 6 divided by 3 would be 2. So that works fine. Just be careful with that. Down here on the bottom, if you're adding or subtracting, especially in a fraction, 12 plus 6 should be 18, and when I divide by 6 there, 18 divided by 6 should be 3. That's the correct answer. But it's real easy on your calculator to go 12 plus 6 divided by 6, and here again, remember order of operations. 6 divided by 6 is 1, and then say 12 plus 1 gives you 13. So just think about what you're putting into your calculator and if that's really what you want it to do. Unit conversions are important. There are a lot of measurements that we do here in physics, and people measure things in different units, and you got to know how to get back and forth between those. For example, if somebody measured 12 feet but they need that measurement in yards, then we'd have to have a conversion factor that gets me from one to the other. These are really easy to do. I'm looking here at these feet that I want to cancel and turn into yards. I'm looking at my conversion factor, and there's feet. So if I take this part, the part that has feet, and put it on the bottom, then the feet on the top cancel the feet on the bottom, and all my feet are gone. Set it up so that the units that you don't want cancel, and the units that you do want are left, and they're in the position that you want. Now when I say 12 feet and feet is on the top, remember we can really kind of put an over 1 there, make it look like a fraction, make it obvious that the feet are on top. And all I have to do is say I've got these two parts, half of it's got to go on the top, half the bottom. Feet on top, put your other feet on the bottom so that the feet cancel. There's the yards on top. I want the yards on top. And again, you can make that look like a fraction, make sure it's on top if you want. Now I got to figure out what to do with the numbers. I see that I've got a 12 and I've got a 3, and that fraction bar right there means divide. If it's on the bottom, you're going to divide, and you'd get 4 yards for that one. Okay, easy conversion, but you gotta remember how to do that. Writing it out like this is your best bet at getting it right. Here's the second one. If we take 15 yards, want to turn that into feet. This time I'd have to take the yards and put on the bottom like that. Oops, sorry, wrong number. Here's my 3 feet. The yards on top cancel the yards on the bottom. Now I've got a 15 and a 3. That 3 is on top. That's a multiplication problem. 15 times 3 is 45 feet. Okay, so that looks like that. Right here I've got another one. This one says 62 miles per hour, and we'd like to turn that into meters per second. So I need to change the miles to meters and the hours to seconds. This is a 2-step process here. The first thing that I need is my conversion factors. I need to know that 1 mile is 1,608 meters. And as soon as I have that, then I can take these miles on top and put the mile on the bottom, and the 1,608 meters on top. The miles on top cancel the miles on the bottom, and I've changed miles to meters, so that's half of it right there. The other thing I need to do is take the hours, change them to seconds, so I'd need a conversion factor there. 1 hour is the same thing as 3,600 seconds. Of course, you got 60 seconds in every minute and 60 minutes in every hour. 60 times 60 would be the 3,600. So this hour is on the bottom. See how there's the fraction bar? Hours on the bottom. I need to put hours on top, so that now these hours on top cancel those hours on the bottom, and I've got 3,600 seconds. And the numbers we have here, I've got a 62, I've got a 1608, I've got a 3,600. The 1608 is on top, so I'm going to multiply. The 3,600 is on the bottom. I need to divide. That's what I want to do. I'm going to go to the calculator here and punch that up. So here is 62 times 1608 divided by 3,600, and I'll get a 27.693333. I don't really need all of that number, and you can get real excited about this and whatnot, but we use this process called scientific notation, and significant figures, and here's the way that works. Let's take it back to what we had, 27.69333. If I write 27.6933333, that looks a little bit silly. In math class we would do that because we're assuming that the 62 is exactly 62, but in physics that's a measured number. Somebody took a car and ran the odometer out 62 miles or something. Somebody pulled off a measuring tape and measured 3 meters or 15 seconds or some kind of measurement, and there's a little bit of human error, there's a little bit of instrument error. These numbers are never exact. So when I take a number like 62 and multiply by this and divide by that and get something that is down here to the what, tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths, 10 millionths place, there's no way I know that number to that level of accuracy. What we do is we call this significant figures, and in physics we don't make a big deal about this. We're a little bit sloppy with numbers, but I need you to understand the principle of it. Basically, this number had 2 digits. There are 2 significant figures there. It wasn't 62.1 or 62.1394. It's just 62. I don't know it any more than 2 digits of accuracy. So this number was part of the conversion factor. So we'll assume that that's exact. That was not something we measured. And the same thing over here, the 3600. Don't count those in your significant figures. The only measured number was the 62. It has 2 significant figures. So I need to come over here. This would be the first digit. Here's the second one. I want to round that number so that I've got 2 significant digits, the same as what I started with. And my choices are pretty much 27 and 28. So if I look at the next digit, I see that that's 5 or greater. So I'm going to round up, and I'm going to say the best answer is 28 meters per second. Okay. Now in here, if you go, well, that's about 27.7 meters per second, I can live with that. But the very best answer is this 28 meters per second. It has the proper number of significant figures, and that would be what you'd want to do. If you had a calculation like 14 times 3.72 divided by 1.6904, okay? If those are all measured numbers, you'd come through and say this has 2 digits, this has 3 digits, this has 1, 2, 3, 4, 5 digits. You want to pick the smallest one. You want to pick the least accurate one. My answer cannot have any more than 2 significant digits because the things that I made that answer out of don't have enough accuracy. I only know it to 2 places. That's the principle behind the significant figures. Okay. Again, I'm not real worried about that, but we can do some of those in class if you want, or whenever. Next up, I wanted to talk a little bit about algebra and remind you of some things. Algebra is really easy. There's only one rule. You can do anything you want as long as you do it to both sides. So in this first problem right here, when I'm looking at this guy and I see that 3 times x plus 4 equals 13, I want to solve for x. I want to get x by itself. Down here at the bottom, I want it to say x equals some number. Okay? So I need to start moving things around. I need to get rid of the 3 that's multiplied by x. I need to get rid of the 4 that's added to the left-hand side right there. You probably remember that it's best to subtract, do your addition, subtraction stuff first. If I subtract 4 from both sides, then I have done the same thing to both sides. And that would be perfectly legitimate. Plus 4 minus 4, those cancel each other out. They add to 0, whatever you want to call it. But I'm left with 3x. 13 minus 4 would be 9. And now I can come through 3 times x. I want to get rid of the 3. The opposite of the multiplication that's done there is division. So I would need to divide by 3. 3 divided by 3 cancels, gives me that x all by itself just like I want. But if I do it to the left side, I've also got to do it to the right side. 9 divided by 3 is 3. There's my answer. You probably know that you can always come back and check and make sure that that works. If I were to take 3 times 3 plus 4, does that really equal 13? Well, here would be 9 plus 4, 13 equals 13. So yes, that worked. That's the right answer. Now, you knew how to do that problem, and you probably know how to do the next one. But I just wanted to kind of do that first one to let you see that we do exactly the same thing with these general formulas. So right here, where it's ax plus b equals c, We can do exactly the same thing. Remember how we did the addition subtraction stuff first? I could subtract b from both sides. B minus b cancels. I'd have ax equals c minus b. What do we need to do now? If I want to get x by itself, I got to get rid of the a. It's multiplied, so I'd have to divide the entire side on the left by a. A divided by a would leave me just x, and I got to divide the entire right hand side by a. Sorry, wrong number. Okay, so I'd be left here with c minus b over a. Being able to work with these formulas in general form like that with no numbers, there are numbers, it's the number a, right? Whatever a represents. The power of symbolic algebra is that we don't know what the number is, but we can still work with it and learn some things that we didn't know. All right, so it's a powerful thing that we can do right there. In this last one, it's a little more involved, but we can still do it. I think we're trying to solve for x right here. Okay, so I got to get rid of a bunch of stuff. This minus 4, I need to get rid of that, and plus 4 would be the opposite of that. But you see how the whole top is kind of tied up with that division bar? I'm taking the entire top. I could even come in here, put some little parentheses around that, and the whole top is divided by 6t. If I could get rid of that 6t, then that would be just grand. The opposite of divided by 6t would be to multiply by 6t. So if I come in here and multiply the left hand side by 6t, and I multiply the right hand side by 6t, that doesn't show up at all, does it? I'll put it here at the end like that. Then the 6t on top cancels the 6t on the bottom. I'd have cx squared minus 4 equals, I'm going to move the 6t up front, and I'd have 4 pi ra divided by 6 plus 8t, like that. I could distribute that 6t in there if I wanted to. Why don't we do that just for kicks? When I take the 6t times the first term, the 6 on top would cancel the 6 on the bottom, so I just have the 4 pi ra, and that t from outside the parenthesis would look like that. When I take the 6t times the second term, I'd have 6 times 8 is 48. T times t is t squared. All right. I didn't do anything on the left, so I'm going to just copy that like so. All right. Let's see what we need to do now. Looks like now that minus 4 is my biggest problem. I could divide by c, but that's going to make a fraction over here and make it hard to subtract by 4. So let's get rid of the minus 4. The opposite of minus 4 would be to add 4. So I'll do that to both sides. It cancels. I get a cx squared equals 4 pi rat plus 48t squared plus 4. Okay, 2 more steps to this. I'm going to divide by c to get rid of that. And I'll just leave the right hand side like it is. And then lastly right there, x squared. I don't want x squared, I want x. The opposite of x squared would be to take the square root, and then the square root and the squared kill each other, and I just have x left over. Alright, if I do it on the left, I got to do it on the right, and I would have that right there. So that would be what I need. Square root 4 pi, just like it shows up there. You can see it. Stuff. Be able to work with those and to move things around. We do a lot of algebra in here. It's good stuff. Very powerful. Next up, I wanted to remind you real quick of a couple things in geometry. The area of a triangle. If you have a triangle, then the area would be that space inside. And how much room do you have to move around in there? The area of a triangle, of course, 1/2 the base times the height. This would be the base, this would be the height right there. Okay. We could also talk about the perimeter of the triangle, the distance around it. So here's my triangle. If I walked here and then walked there and then walked there, then I'd need to add those 3 sides. Why don't we call the third side C there? Okay. And usually when we write the perimeter, we call this A, call it H, I don't really care. But we're just going to walk all three sides there. It's the sum of the three sides. If you walk 20 feet and then 25 feet and then 4 feet, you'd have to add those together to get that. If we're talking about a rectangle, then we'd have a length and a width. And the area, the space inside here, would be the length times the width. And the perimeter, the distance around it, would be length plus width plus length plus width, right? That would get me all the way around this shape like that. So we could boil that down and say 2L plus 2W would be a little bit tighter right there. Circles are pretty handy things. We use them all the time. And generally there's a radius specified like that. The radius would be the distance from the center of the circle to any point on the edge on the circle itself. And the area, the space inside that circle, is given by pi r squared. The distance around the circle, now called the circumference, is 2 pi r. So those are kind of handy, and I'm sure you've seen those before. You probably remember those, but just kind of wanted to toss them out there. Next up, I've got something called trigonometry. You don't need to know a whole lot about trigonometry here. We're going to work through it, kind of assuming that you've never seen this before. But there's no magic here. It's really neat. It's really powerful. It's not magic. All you got to do is you got to think about the three sides of the triangle. And this is all right triangle trigonometry. I'm only thinking about triangles that have a right angle in one corner. You can see that right here. That little square means that's a 90-degree angle, a right angle. Generally there will be one other angle involved, and we call that theta. This is the Greek letter theta, which just means angle. We use it to represent that angle. Could be 40 degrees, 22 degrees, 273 degrees, something like that. But as soon as I see my triangle and I know that that's theta, then I'm going to look to the opposite side over here and refer to that side as the opposite. And we abbreviate opposite down OPP. Okay? The side right next to this guy down here, here's my angle, and right next to the angle is the adjacent, ADJ. And then of course the long side over here already has a name. We refer to that as the hypotenuse, which we're going to abbreviate down to HYP, and it's always straight across from the right angle. Okay? You got to be able to label those sides. Theta is in one corner, the opposite straight across, the adjacent's right next to theta, the hypotenuse is straight across from the right angle. So those are the names of those three sides. And as soon as you have the names, then you can define three trig functions. And these are really easy to work with. Functions. And the first one is referred to as the sine of the angle. We abbreviate that down to SIN. And all you got to do to take the sine is to take the length of the opposite and divide by the length of the hypotenuse. If the opposite is 3 and the hypotenuse is 5, then you're just saying take 3 divided by 5. The beauty of this thing and the simplicity of it and the power of it is that the length of this side, the opposite, and the length of that side lock in this angle. If I've got 3 here and 5 there with a right angle, there is only one angle that can sit right there. And if I put a bigger angle, let's say the angle goes on up to, say, here. You see how the opposite had to get bigger? And there the hypotenuse probably actually got bigger too. It changed it. The shape of the triangle determines the ratio of the opposite and the hypotenuse determine that angle, or the angle determines the ratio of the opposite and over the hypotenuse. However you want to say that, that's all we're talking about here. When you do the second trig function right here, this is called the cosine, and abbreviated down to COS theta. and that's adjacent over hypotenuse. And you probably know that 3, 4, 5 makes a right triangle. That's the world's most famous right triangle right there. So I'm gonna call that a 3, 4, 5 triangle. We're not talking about the this wackadoo line that I drew right there, this wackadoo angle right there. Talking about the regular old hypotenuse there. If I take the length of this side, 4, and divide by 5, there's only one angle that will fit right there if I've got a right angle coming in here, and the cosine would just simply be 4/5. It's just a dumb old number, okay? The last one then is the tangent of theta, and that's equal to tan theta, the abbreviation, and it's always opposite over adjacent. Okay, which in this case would be what? Opposite is 3, the adjacent's 4. Okay, the part I really need you to know is all this right here. Okay, those are the 3 definitions. That's what you need to write down. Let me go ahead and tell you that you do get an index card that you can bring to each and every test. It could be a different card for the second test, third test, whatever. But you do get to bring an index card. Maybe those 3 functions are important enough to where you don't want to forget them, and you do want to write them on your index card. But it's up to you. Maybe you're comfortable with that. Let me show you a couple problems here that illustrate how useful these things are. And I have forgotten how to. Here we go. Let's take a right triangle. Let's say that I measure, here's a telephone pole, all right? Got a telephone pole sticking up in the ground. We want to go buy enough cable to reach from the top to meet down here at the ground, and we want that to be a 30-degree angle. Okay? If I know my telephone pole is 43 feet, then the question is, how much cable do I need to buy right there to reach down? Okay, the first thing that I always have to do with these is to label my sides. So this would be theta. That's the angle they gave me, the angle of interest. Straight across is the opposite, and of course this is the hypotenuse. So I need a trig function that has opposite and hypotenuse in it. When I go back, I see that sine is the one that has opposite and hypotenuse. So I want to use that trig function right there. Sine equals opposite over hypotenuse, and then I can make this thing work out for me. Figure out which sides you have, which 2 sides you're interested in, and then work out your pick the trig function based on those 2. In this case, opposite and hypotenuse. I want this thing right there, the hypotenuse. I got to do a little bit of work moving these things around. Again, here's the algebra that we need to be able to do. That hypotenuse is on the bottom. If I use algebra, this may seem a little bit, whoa, can I undo that? Thank you. This one. If I do some algebra here, just play along with me for a second. If I come through and multiply both sides by the hypotenuse, that would be doing the same thing to both sides. The hypotenuse on the top is going to cancel the hypotenuse on the bottom, so I get that. The opposite is equal to the hypotenuse times the sine of theta. Now I want the hypotenuse by itself. I want this guy to sit all by itself. That sine's in my way, so if I come through here and divide by the sine of theta on the left, it cancels. Then I'd have to do it on the right as well. What I want to do is take the opposite, which is 43 feet, divide by the sine of the angle, which was 30 degrees. That should give me the hypotenuse, the length of the cable that I need to go to the store and buy. Okay, so let me go find the calculator here, and we're going to do 43 divided by the sine of 30 degrees. I hit on, I go 43 divided by sine 30, enter. Now here again, remember that mode, I'm in degrees, I'm all good. Okay, my answer I need 86 feet of cable. Okay, so that's some powerful mathematics right there. I don't know any other way to get that number. Algebra won't do it. Calculus won't do it. You need trigonometry here. We use a lot of trig in here, so we can do more of those some other time, but that's the idea with that. Okay, I want to talk real quick about formulas and the way that they're stacked, the way that they're arranged. Anytime you see a formula that has this kind of form, where there's a variable here and there's a constant there and you get something else, that's a direct variation. If I put a bigger number in x, I get a bigger number in y, right? So if this one goes up, that one goes up. In physics, we're trying to find the patterns of the universe. We want to know what's going on. How does this work? And when one thing changes, how does that change something else? And the direct variation is kind of the simplest model of that. Now, if we were to just make up some numbers here, let's say that x and y. If I put a 0 in here, 4 times 0 would be 0. If x is 1, 4 times 1 would be 4. If I let x be 2, 4 times 2 is 8. And we could just do this all day long. If we drew those pictures, we'd get that line. We'd get this graph. So anytime you see a graph that looks like that, you're pretty sure it's a direct variation, and that there's a direct variation. As this variable goes up, that one goes up. And this is kind of a dumb example down here, but if I had a little vendor cart and I was walking through the park selling stuff, if I had ice cream in my cart, when the temperature goes up, I would expect the ice cream sales to go up, right? The hotter it gets, the more people want ice cream, and the more I sell. Now, the other possibility here that I wanted to mention was the indirect or inverse variation, and it's going to fall off. It's got this form right here, where y equals some number divided by x. The variable is on the bottom. When I put a bigger number, when I divide by a bigger number, I'm going to get a smaller answer, and it's going to fall off like that. So again, kind of dumb example, but if I were selling winter hats, toboggans, beanies, mittens, whatever, in my cart, the hotter it gets, the less people want that stuff, and my sales are going to go down. It's an inverse variation. The reason I mention this is if you see a formula and it has some kind of form like, well, here's one. This is actually a formula that Isaac Newton cooked up. It's about how much force there is between two objects when gravity is pulling. Can you see that this is a constant that we toss in right there? That's effectively that 4. But M1, that's the mass of the first object, could be the moon. M2, mass of the second object, could be the earth. Those are on top. So when I make those masses bigger, that makes the force bigger. And down here, I've got the distance between those two objects. When that gets bigger, the force gets smaller. That makes sense. It's even an inverse square law. So as the distance between them gets bigger, the force really gets smaller. If I double the distance, I fourth the force between them. It's a fourth of what it was before. So just kind of look at formulas and think about how they work and what's going on with that. Okay? And thank you very much, and hope this makes sense. These videos, of course, can be sped up or slowed down or watched whenever you want or as many times as you want. I hope they kind of help you get through this. You need to go ahead and work the LOP, the question answer problem. There's some problems in D2L, and you work those and answer those questions and kind of practice what we've talked about here. If you have questions, then you need to email me or call me or see me or something. Come to class, office hours, whatever. But let me know how I can help. Thank you very much.